Hello everybody. This lecture is about solving the numericals on rectifiers. So let us start with this circuit diagram. Uh, it is a step down transformer with 5:1 ratio. At the primary side 120 volt 50 hertz AC signal is being applied. A diode is connected. Since it is a single diode, this is nothing but a transformer connected half wave rectifier, and RL is the load of value 1 kilo ohm. So given this circuit, you need to calculate the peak load voltage and DC load voltage. So peak load voltage and DC load voltage, these two are requisites. DC load voltage, these two needs to be calculated. Now since the transformer is having 5:1 turns ratio, it means that the RMS secondary voltage is 1/5 of the primary voltage, because it is a step down transformer. RMS secondary voltage is 1/5 of the primary voltage, and primary voltage is 120 volt. So V1 is the peak primary voltage, V2 is the peak secondary voltage, and it is expressed in with their RMS values. So we can find V2 as 120, which is V1, divided by 5, because it is 5 times less V2 than V1. So that means it is 24 volt. And the peak secondary voltage, so therefore the peak secondary voltage, if V2 is 24 volt, it is given by, suppose it is denoted by Vm, the peak secondary voltage, it is denoted by the given value V2 divided by 0.707. That means, because since V2 is equal to Vm by root 2, if Vm is the peak value, Vm by root 2 is the RMS value, and V2 is the RMS value of the secondary voltage. So we should calculate from here 24 by 0.707, that is 34 volt. Now if this diode is an ideal one, there will not be any, it will conduct right from the 0 volt during forward bias, and no question of knee voltage or the cut-in voltage is there, as 0.7 volt that is required. So in this case, for ideal diode, the peak load voltage is given by this 34 volt. So for ideal diode, Vp out, peak load voltage, output voltage is 34 volt. It is already found. And considering this, the DC load voltage will be VDC, denoted by VDC, that is equal to 34, you know what is that, Vm by pi. This is the formula. That means 34 divided by pi, that means 10.8 volt. Now if it is a non-ideal diode, considering the second approximation, that means considering the cut-in voltage of 0.7 volt, considering as a silicon diode with cut-in voltage of 0.7 volt, if we incorporate in this data in the calculation, then this Vp out, peak output voltage or peak load voltage, will be 34 minus the drop of barrier potential, that is 33.3 volt, and therefore in that case VDC will be changed, it is Vm by pi accordingly, that is 33.3 divided by pi, that means it is 10.6 volt. So these are the answers for non-ideal case, and these are the answers for ideal case of diode. So this is the first simple example of solving a problem on half wave rectifier. Now let us look at the second problem. So this problem says a diode with internal resistance of 200 ohm is to supply power to a 1000 ohm load from a 300 volt RMS source of supply. You have to calculate peak load current, DC load current, AC load current, DC diode voltage and input power to the diode. So let us look how this problem can be solved. From the given statement, you can see that this is a problem on half wave rectifier, because one diode is being used for rectification and the peak value of supply is given by solution Vm peak value. This is peak value of supply. You need to keep the need to find the peak value first, because the RMS value of 300 volt is given. So if you want to calculate Vm or peak value of supply, it is once again, as we have calculated in the likewise we have calculated in the previous example, it is √2 multiplied by the RMS value. To find RMS value, you need to divide by √2, and to find the peak value you need to multiply by √2. This is the thumb rule. So this is 424 volts. Now the first part of the question, peak load current, you need to calculate. So for a half wave rectifier, peak load current denoted by Im, suppose, is given by Vm divided by Rf plus RL, where RL is obviously the load resistance which is given in your problem, 1000 ohm, and Rf is the forward resistance of the diode, that is the diode internal resistance, which is given as 200 ohm. So if we put here 424 divided by 200 plus 1000, it is given as 0.353 ampere. So this is our first calculation, first part. Second part is you have to find DC load current. DC load current denoted by IDC, you know by the formula Im by pi. So it is Im already we have found 0.353 by pi. Pi means it is 3.142. You need to put and calculate. You will find 0.112 ampere. So this is the second part of the problem. The third part is you need to calculate the RMS value of the AC load current. You need to calculate AC load current. That means you need to calculate the RMS value of AC load current, and it is denoted by IRMS dash. It is RMS value of AC load current, and it is given by IRMS square. The formula we have found this formula in the derivation part of ripple factor. We have seen in one of our last lectures. IRMS dash can be written by IRMS square minus IDC square whole to the power half. This was the expression. You can once again recapitulate to find this formula over there, where RMS value of load current, IRMS, also we have found over there, and that IRMS is nothing but Im by 2, as we have found in the derivation previously. So Im we have already found 0.353 divided by 2, and so this is 0.176 ampere. So now we have in our hand IRMS and IDC. Substitute the values to find. Therefore IRMS dash is 0.176 IRMS square minus IDC square, which was 0.112 whole square whole to the power half. So it will give you, after calculation, 13.1356 ampere. So this is our RMS value of AC load current, the third part of our calculation. The fourth part is the DC diode voltage that is being generated by the conduction of the diode, denoted by VDC, which is can be written by IDC, generated by the, since it is generated by the diode, so diode is conducted with a current IDC and the diode resistance is RF already given. So if we multiply IDC into RF, V equal to IR, just simply applying the Ohm's law for the diode, we can calculate 0.112 as IDC into 200 ohm. This is 22.4 volt. So this is the DC diode voltage by the application of simple Ohm's law. And the last part of calculation is total input power. Total input power to the diode, denoted by Pi, is given by, we know power means P equal to I square R, simple formula between power and current. So now we have, as we have calculated this I through the diode and RF is given, the diode resistance, we can easily calculate Pi, the input power to the diode. The current is obviously, input power means the current is obviously having some AC component, so we should be considering IRMS and not IDC. Just check the dissimilarities between these two calculations. Since this is DC diode voltage, that means it is indicating the output of the diode, and output of the diode is primarily having DC components, but at the input of the diode it is primarily having the fluctuating components, that is the AC components, and AC component means you need to consider the RMS values. So at the output, for output calculation we have to consider IDC, and for the input calculation we have to consider the IRMS. So for input power the current will be IRMS, and we have calculated IRMS already here, 0.176 ampere. So it is IRMS square into RF plus RL, the total resistance in the circuit through which the IRMS current is flowing. So from here we can calculate the input power, 0.176 whole square IRMS, 200 plus 1000 the resistances, and this will give you 37.17 watt. So this is the fifth part of the problem. Now if we want to calculate at the same time the output power also, that is PDC, we can also calculate. In that case we need to consider IDC and not IRMS, because the output of the diode will be DC primarily. So IDC square into RL, and that output is flown into only the load resistance. At the output of the diode there will be no question of considering the resistance, internal resistance of the diode. So the resistance part will be having only with RL. So IDC square RL is the, this is the output power from the diode, or output power at the load, rather we can say, from the diode. So if we calculate this one, 0.112 whole square into 1000, that is 12.544 watts. So this is all about the problem number 2. Let us see the problem number 3. So this problem says it is a problem on full wave rectifier. It consists of two diodes of each of forward resistance of 500 ohm. The rectifier supplies power to 2000 ohm resistive load, primary to, so the load resistance is given, primary to secondary turns ratio is given as 11:28, and it is a center tapped configuration. RMS value of primary input supply is 220 volt. All these data is available. Now you need to calculate DC load current, direct current in each diode, AC component of voltage across the load, and DC output power. Now we know that in the solution, let us come to the solution, we know that if for a transformer, if Vp and Np we consider the RMS voltage and the number of turns of transformer primary, this is RMS voltage and this is number of turns at the primary side of a transformer, suppose, and Vs and Ns likewise the same in the secondary side, that is the RMS voltage and the number of turns. Then from the concept of transformer we can write Vp by Vs is equal to Np by Ns. So in the problem it is given as 220 volts is given as Vp. So therefore we can calculate, and Np by Ns is also given as 11 by 28. So from here we can calculate Vs as Vp into Ns by Np, that is 220 into 28 by 11, that is 560 volts. So this is the RMS value at the secondary side, RMS value of voltage. The secondary transformer voltage to the center, since it is center tapped, so because of center tapping, secondary transformer voltage to center, so secondary transformer voltage will be how much? To center, half of this value, that is 560 divided by 2, that means 280 volts, and this is also the RMS value from either side of the transformer up to the center. So therefore the peak value of voltage to the diode, any of the diode will be how much? Root 2. You have to multiply it by root 2 with the RMS value, that is 280, which we have found, that means 395 volt. So the peak current through the load resistance, so if this is the voltage, peak value of voltage, so therefore peak current should be denoted by Im, that is Vm by Rf plus RL. Likewise we have seen in the last problem of half wave rectifier the same formula. Now Vm is 395 volt divided by the value of Rf is 500 and RL is 2000. So if we calculate, it is 0.158 ampere or 158 milliampere we can say. So this is the first part of calculation of Im. Now once Im is available with you, now calculate the first part of your problem, DC load current. DC load current will be how much? IDC in this case for a full wave rectifier. 2Im, the formula is 2Im by pi for full wave. If it is half wave, it is Im by pi, and if it is full wave, it is 2Im by pi. Now Im is available, so 2 into 0.158 divided by pi means 3.142, and this will come as 105.58 milliampere. The second part, the calculation of the second part, the total load current is supplied by the two diodes in this case, unlike the previous one where it is only one diode present because of half wave rectification. So the DC current supplied by individual diode will be how much? If this IDC is the DC load current, it is supplied by both the diodes. So individually we need to calculate the individual diode current. So individually DC supplied by each diode, individually DC current supplied by each diode will be how much? IDC divided by 2, because of full wave, so it will be 105. IDC how much? 105.58 divided by 2, it is approximately 52.79 milliampere. Now third part of the question, AC component of voltage across the load. AC component of voltage across the load is IRMS dash into RL. IRMS can be written as IRMS dash can be written as IRMS square minus IDC square whole to the power half into RL. This is AC component of voltage, that is calculated like this, I into R, and that I is IRMS dash, and IRMS dash means this value we have seen from the previous example, this value. Now here IRMS, it will be calculated likewise Im by root 2 for a full wave rectifier, full wave, this is the formula. And Im we have calculated Im as 0.158 ampere. Here this one by root 2, and this is 111.72 milliampere. Now put this value here, and IDC we have already calculated. So what is this AC component of voltage across the load? IRMS dash RL is equal to 0.11172 whole square minus 0.10558 whole square whole to the power half into RL, this RL which is 2000 ohm, and this will be approximately 73 volt. The fourth part of the calculation, DC power available at the output. How much? Denoted by PDC. The formula is IDC square RL. We have already discussed about this. Why? Because at the output primarily the DC component will be present and the signal will be supplied to RL only, and no question of internal consideration of internal resistances of the diodes. So it is only RL, not RF, and the supplied current is IDC at the output, so I square R. The output power, DC power available at the output. Now IDC we have already calculated, this is 105.58 milliampere, so convert it into ampere, it means 0.10558 whole square into 2000, that is equal to 22.29 watt. So this is the input power, output power available at the output. So this is the solution of the third problem. Now let us see the solution of the fourth problem. So the third problem says it is a bridge rectifier, that means it is consisting of 4 identical diodes, produces a direct current of 124.49 milliampere across a 2000 ohm resistive load. So this is the DC output current. If RMS value of primary input supply is 220 volt, we need to calculate primary to secondary turns ratio of the transformer if each diode has forward resistance of 10 ohm. Now for a full wave rectifier, since bridge rectifier is also a full wave rectifier, we know the solution should be like this. For a full wave rectifier, the DC load current is given by IDC. Because the DC load current is given, the formula we can directly write, so that we can put the value of direct current at the output, which is IDC 2Im by pi. From here we can calculate the Im is the peak value of the load current, and since in bridge rectifier two diodes connected in series conduct simultaneously, you know, so the peak current Im is given by, in a bridge rectifier, it is Vm by 2Rf plus RL, because at a time two opposite arm diodes, you know, two opposite arm diodes in a bridge rectifier at a time conducts, and the diodes in the other two opposite arms remain in off condition or open condition. So for two at a time conduction, internal resistance of those two diodes are considered along with this load resistance RL, and this is the useful formula. We have already used this formula in the last two problems. So from here we can calculate the value of Vm using these two formulas. First, from this formula, this IDC is already given. From here we can calculate Im, and putting that Im over here, Rf and RL, we can calculate Vm. So what is Vm? Vm is the peak voltage across the transformer secondary. So Vm is peak voltage across secondary. Rf is the forward resistance of the diode and RL is the load resistance. Now if we combine the last two equations, we can write IDC equal to 2Vm by pi into 2Rf plus RL. So from here we can calculate Vm, which is half pi IDC whole into 2Rf plus RL. Now put all the values. IDC is always already given in the problem, 124.49. Rf and RL is also given. So if you put all those values, from here you can calculate Vm, that is half into 3.142 into IDC is 124.49, 2 into 10 plus 2000. Putting all the data and calculate, you will get 395 volt as Vm. Now let us consider Vp and Np. Likewise, in the last problem, likewise the voltage and the number of turns, this is obviously RMS voltage, and the number of turns at the primary side. This is at the primary side of the transformer. This Vp, this is peak RMS voltage, peak, and Vs and the peak secondary voltage we have already calculated, it is 395 ohm, that is Vm and Ns are the same for secondary side of the transformer. So we can write